Hello student, and welcome to BEG 2205 Analogue Electronics I. My name is Miriam Kinene. Our topic today is Introduction to Semiconductors. That gives our lesson outline. So we are going to look at definition of a semiconductor and its properties. We shall also review on N-type semiconductor and P-type semiconductors. We shall look at the PN junction and its VI characteristics, and also look at the semiconductor diode as a rectifier. To start with, start by defining what is a semiconductor. You can say it is a substance that has conductivity between conductors and insulators. Conductors are those materials that are able to conduct electricity. Insulators are materials that do not conduct electricity. Examples of conductors are metals. Insulators, examples are wood, glass, etc. So we look at the properties. Property number one is that a semiconductor has a resistivity in between insulators and good conductors of electricity. Number two, they have negative temperature coefficient of resistance. Negative temperature coefficient of resistance means that if you increase the temperature of a semiconductor, then its resistance decreases. For metals, usually they have a positive temperature coefficient of resistance, because if you increase the temperature for a good conductor, or rather for something like a metal, then you realize that the resistance increases. But with the semiconductors, they have negative temperature coefficient of resistance. Property number three is that if you had an impurity to a pure semiconductor, usually you increase its current conducting property. So its conducting property is increased appreciably by doping. Doping usually is the process of adding impurity in controlled amounts to a pure semiconductor in order to increase its conductivity. So P-type semiconductor is formed by doping a pure semiconductor with a trivalent impurity. So we are saying trivalent impurity is the one that has 3 electrons in the outermost shell, or rather in the valency shell. So our semiconductor, remember, has 4. So if we can look here at an example of semiconductor is silicon and germanium. So silicon and germanium are the mostly used semiconductor, and that's because they require less energies compared to others for an electron to move from valency band to conduction band. So if, for example, we consider silicon is atomic number 14, and therefore it means that its electronic configuration is 2, 8, 4. So with 4 electrons in the outermost shell, it's usually a silicon crystal will form a crystal by forming what we refer to as covalent bonds. So if you take a pure silicon, remember we want to form we want to see how P-type is formed. Pure silicon, and you dope it with a trivalent impurity such as gallium. Gallium usually has 3 electrons in the valency shell. The silicon atom will fit into gallium atom in such a manner that it will form covalent bonds, as illustrated here. So assuming this is our gallium, then we'll have the silicon forming some covalent bonds. So gallium, remember we have said it has 3 electrons like that. So we'll have here a silicon contributing 1 electron, another silicon atom contributing 1, another silicon atom contributing 1, and also here another silicon atom contributing 1 electron. So you can see that as these silicon and germanium atom forms covalent bonds, only 3 covalent bonds can be formed. If you can look at this particular point here, you can see it's only silicon that is contributing. Gallium is not contributing, and therefore there is an absence of an electron, which we call an hole. So addition of a little amount of gallium into silicon results into millions of holes in that particular crystal, and what is formed is actually what we refer to as a p-type semiconductor. Now, n-type semiconductor, on the other hand, is formed by doping a pure semiconductor with a pentavalent impurity. It's doped with a pentavalent impurity. A pentavalent impurity has 5 electrons in the outermost shell, and we know our semiconductor has 4 electrons in the outermost shell. So we can consider maybe germanium. This is the semiconductor, and then we can also have arsenic, which is a pentavalent impurity, So addition of arsenic into germanium forms what we refer to as the n-type semiconductor. Reason being, the germanium atom fits into arsenic in such a manner that it forms covalent bonds. So assuming this is our arsenic, we are saying it has 5 electrons. Can just draw them. 1, 2, 3, 4. Then our 5th one there. Can put it there. And then we are saying these germanium atoms will fit into arsenic. Let's assume that is our germanium contributes 1. This other one contributes 1. We also have another germanium contributes 1. Another here, germanium contributes 1 electron. So you can see 4 covalent bonds have been formed, and 1 extra electron finds no place in the covalent bond. So this is a free electron. So these free electrons, electron is available for conduction. So addition of a very small amount of pentavalent impurity results into millions of electrons formed that are responsible for conduction in n-type semiconductor. Now let's look at what is a p-n junction. A p-n junction can be defined as a single crystal semiconductor material in which one region is doped with acceptor impurity atoms to form the p-type region, and the adjacent region is doped with donor atoms to form the n region. Or you can simply say it is the interface at which the p-type silicon and the n-type silicon make contact with each other. So what is represented here in this diagram? It's actually the p-n junction. This is the p-type material. This is the n-type material. Both are semiconductors. So with the p-type material, remember, this has holes, and the majority carriers here are holes, and with the n-type material, majority carriers are electrons. Remember, we are talking about majority because even at room temperature, there are some of electron hole pairs that are usually created. So when you dope, for example, the p-type, what you're increasing is the holes. but those electrons that were still liberated at room temperature still remains. So they are minority carriers. In the N-type, majority carriers are the electrons. Minority carriers are the holes. So that is p-n junction. Okay, now we look at the properties of p-n junction. Now, at the instant of p-n junction formation, and that occurs when actually at manufacture. So at the instant of p-n junction formation, free electrons near the junction in the N region will diffuse across the junction and therefore combine with holes in the p region near the junction. And as a result, the p-type material near the junction attains a negative charge. So diffusion of electrons from the N side also creates a localized positive charge on the N side. So this is what we are talking about. We have, at the time of manufacture, we are saying, or at the instant of formation of the p-n junction, we are having this is the p-type, this is the n-type. So the n-type, we are saying we have electrons, which are the majority carriers. Here we have holes, we can represent them by that. So we are saying what happens is that electrons from the n-type will cross over to the across the junction and come to the p side like that. Similar, and once they cross over, what is created on this side, assuming this is our junction here, what is formed here is some positive charges like that near the junction. What is formed is positive charges near the junction. So as they try to recombine with the holes, again, negative charges are created on the other side of, that is the p region, like that. So that is how that is what actually is formed when electrons diffuse across the junction to come to the p. They recombine with holes, form negative charges, and on this side, localized positive charges are also formed on the n side. So these two layers, you can see there are two layers of charges. These two layers of charges form the depletion region. The term depletion is due to the fact that near the junction, the region is depleted of charge carriers, that is the free electrons and holes, due to diffusion across the junction. So this is actually what we are talking about here, as electrons and as electron diffuse, as charges diffuse across the junction, whatever is formed here is a depletion region. So once the junction is formed and depletion layer created, the diffusion of free electrons stops. In other words, the depletion region acts as a barrier to further movement of free electrons at the junction. And as a result, whatever is created here is what we refer to as a potential barrier. So potential barrier here will not allow further movement of electrons or changes across the junction. So the separation of these charges is what we are referring to as the potential barrier. So the potential barrier must be overcome by external voltage source to make the junction conduct. So the way it is, with this barrier, it cannot conduct unless, because these serves as some little potential difference. So because of this PD, or the potential barrier here, there is no movement of charges. So in order to ensure movement of charges, that's now when you are talking about external voltage. And external voltage that must be allowed should be able to overcome this potential here. For silicon, if this PN junction maybe was of silicon, then the external voltage to overcome that for silicon is usually 0.7 volts. For germanium is 0.3 volts. It's 0.3 volts. So depletion layer is formed very quickly and it is very thin compared to the N region and the P region. Now this here diagram here represents the symbol of a PN junction. We can also call it the crystal diode. That forms this actually is the symbol for crystal diode. Now let's look at biasing a PN junction. Biasing a PN junction. Remember we have said that the potential barrier here does not allow movement of charges. So unless you apply an external voltage that can be able to overcome the barrier, then movement of charge carriers is not possible. So we come to biasing of a PN junction. We have forward biasing. In forward biasing, an external DC source of voltage is applied to the junction in such a manner that it cancels the potential barrier and thus permitting current flow. So this is what we are talking about. If this is our PN, P, so assume that our P side and this is our N side, we want to forward bias, then usually the P side is connected to the positive terminal of the battery and then the negative side is connected to the negative terminal of the battery like that. So V is our external source voltage. So when you apply this voltage in such a direction, then it reduces the width of the depletion region and thus allows current to flow. Remember we said that this region here, for silicon, it will require roughly 0.7. So the initial voltage, when you apply, this voltage must be overcome first before the device can start conducting. Now, we can now look at reverse biasing. With reverse biasing, external DC voltage is applied to the junction in such a direction that the height is increased. When you apply voltage in reverse direction, this being our P and this our N, then P is usually connected to the negative and N to the positive like that. So if you connect like that, then your barrier height here is increased. Your barrier height is increased. Your barrier height is increased. If your barrier height is increased, then what follows is that the resistance of the PN junction also increases. And if the resistance increases, then it means that no current flows through the junction. So this is forward biasing. This is reverse biasing. That is reverse biasing. Next, we look at the VI characteristics of a PN junction. The VI characteristics of a PN junction. So VI characteristics actually refers to the curve between voltage across the junction and the circuit current. Usually voltage is taken along the x-axis and current along the y-axis. But before we go to the characteristic itself, we can look at this diagram represents the test circuit. So for example, the way that this is connected, we can see this is our positive terminal. We have a switch here just for switching on the circuit. Once you switch on, you can be able to vary. These are variable resistor that can be able to vary the input voltage to our PN junction here, or our PN diode. So this is just a current limiting resistor. We have an ammeter here to measure the current. Remember, we are plotting voltage against current. So here the ammeter is used to measure the current. Voltmeter, which is connected in parallel like this, is used to measure the voltage. This measures the current. So it's usually connected in series like that. So this is just a test circuit. So we can now look at the characteristic itself. Now, that represents now the VI characteristics of a PN junction. That represents the VI characteristic of a PN junction. Now, you can notice that we have this particular portion here and this particular portion here. We talked about forward biasing and reverse biasing. When you forward bias, you are reducing the potential barrier, and therefore you allow current flow. So this is our forward biasing bias region. This is our reverse bias region. And of course, we have current in milliamperes in the forward current. Our forward voltage is given in volts, and then the reverse currents we are giving in microamperes. So at zero external voltage, we're just going to, I can maybe, for the sake of explanation, can just quickly sketch that diagram we've just seen in the previous slide here. So that represents our VI characteristics. So I want to explain now the characteristic. With zero external voltage, when we have not applied any external voltage to the diode, that is, when the circuit is open at K, maybe you can go back to the circuit. This is open, so we don't have any voltage applied to the PN junction. So when the switch here is open, we have zero external voltage. The potential barrier at the junction does not permit current flow, and therefore the circuit current is zero. So you can notice here, we have here at zero external voltage, we are at some point there. So no forward voltage applied, then circuit current is zero. Circuit current is zero. With number B, with forward bias now. With forward bias to the PN junction, that is the P connected to the positive terminal and N connected to the negative terminal, the potential barrier is reduced. And we had mentioned that for silicon, it's 0.7 volts, and for germanium is 0.3 volts. So the potential barrier is altogether eliminated, and current starts flowing in the circuit. So when you when the forward voltage is increased, you can see maybe from particular point from here, let's call this 0, the origin 0, and some point here we can call it A. So you can notice that in this curve between region O and A, the curve is somewhat nonlinear. It's nonlinear because the forward voltage that is applied in the initial stages is used to overcome the potential barrier. So you may notice that immediately after the potential barrier, maybe this is, let's assume this was silicon, 0.7 volts. After the potential barrier has been eliminated, then you can see the increase in current through the PN junction is in direct proportion to the applied voltage, or rather we can see it obeys the Ohm's law. So this means that the barrier has been completely eliminated, and therefore that's why the current increases in proportion, in direct proportion to the increase in voltage. And this is our forward characteristic. Forward characteristic. And at this particular point here, whereby our current starts to increase with direct proportion to voltage, usually referred to as the knee voltage. Next, we look now at reverse bias. So with reverse bias, remember we said that we apply external voltage in such a direction that it increases the potential barrier. So P-type is connected to the negative terminal and N-type connected to the positive terminal. So with that, the potential barrier is increased at the junction. So when the potential barrier is increased, it means that the resistance of the junction is also increased. So the resistance becomes very high and practically no current flows through the circuit. However, in practice, a very small current will flow, and this current is due to minority carriers in the circuit with a reverse bias. So if you can look at this, with reverse bias, you may notice that this is there is a small current from here up to here. There is a small current which remains substantially almost constant. Even as you continue to increase the reverse voltage, it does not increase. This small current here that flows is usually due to minority carriers. So with the reverse bias, practically there is a small current due to minority carriers. So if the reverse voltage, there is a limit in which if you reach that, you exceed that limit, then what happens is breakdown of the junction. So breakdown voltage is the minimum reverse voltage at which the junction breaks down with sudden increase in reverse current. So at this particular point here, we are having our breakdown voltage. At this particular point, we can have the breakdown voltage there. So if you continue to increase, there is a point in which the PN junction cannot be able to withstand the reverse voltage, and therefore it breaks down, and that is accompanied by a flow of large current through the diode. It's accompanied by flow of current through the diode, and that is the sudden rise in reverse current as illustrated here in our graph. So we had also mentioned that knee voltage is the forward voltage at which the current through the junction starts to increase rapidly. At this particular point here, can just label it. This is our knee voltage. Okay, now we look at forward resistance of a diode or the PN junction. So when we talk about the forward resistance, it's actually the resistance offered by the diode to forward bias. We have two types here, the DC forward resistance, and this can be defined as the opposition offered by the diode to direct current, and it is measured by the ratio of the DC voltage across the diode to the resulting DC current through it. We also have the AC voltage resistance, and this is the opposition offered by the diode to the changing forward current, and it is measured by the ratio of change in the forward voltage across the diode to the resulting change in the current through it. Then we have resistance, the reverse resistance of the diode. And this is the resistance offered by the diode to the reverse bias. And it can either be DC reverse resistance or AC reverse resistance, depending upon whether the reverse bias is direct or changing voltage. So we can also look at diode models, and we have 3 models that I'm going to explain. One, we have the approximate equivalent circuit. Approximate circuit equivalent. Then number 2, we have the simplified. We have the simplified circuit. And then number 3, we have the ideal model. Number 3, the ideal model. Now, with the approximate circuit equivalent model, the diode can be represented as something like this. Whereby this represents the voltage across the diode, we can call it VF, and this as the resistance, and that as the resistance of the diode. So, sorry, I want to make a correction here. The approximate circuit equivalent can be represented as this, whereby from here up to here, we measure the voltage across the diode, but then you realize that the approximate circuit equivalent has a V naught here and RF. And because of RF, there is usually a voltage drop as current flows. So we can say our VF, or rather the voltage across the diode, will be equal to V naught plus IRF. That will be the voltage across our diode. Now, with the simplified circuit, we have something like this. We have something like that, whereby in most applications, the value of RF is usually ignored because it's actually a small value. So what we represent here is just the voltage across the diode VF. In the ideal model is whereby the diode is considered as just like another conductor, and therefore no voltage drop across it. So with the ideal model, it's rarely found, but when it comes to circuit analysis, it's usually used. When it comes to circuit analysis, the ideal model is usually used, and it's just considered as just like another conductor. Simplified model, we only have VF, whereby the internal resistance of the diode is ignored. So this is majorly used. The approximate circuit equivalent is RF. Next, we look at the crystal diode as a rectifier. Now, because we've seen that a diode, from the characteristics, it conducts current in one direction. When you reverse bias, the resistance becomes I and it is not able to conduct. That serves as an important feature when it comes to rectification. Rectification is whereby AC power is converted into DC power. Can use just a small diagram here, maybe of half-wave rectifier circuit to just show how this happens. So this being our AC source of power, we have maybe a transformer to step down the voltage, and then have our diode here, and probably our load. If this is a load that requires DC, because at the input here is a sinusoidal waveform. This sinusoidal waveform is the one that is from our AC source. So we have the step-down transformer which steps down voltage, then our diode which converts, which serves as our rectifier, converts AC into DC. So during the positive cycle, this point here is positive, this point here is negative. So the diode will be forward biased and it will conduct. So our voltage will be measured across the load. So during the positive half cycle of the input, we will expect an output. During the negative cycle, during this cycle here, this point here now becomes negative and this positive. So the diode is reverse biased. So during this cycle, the diode will be reverse biased and therefore it will not conduct. So up to that point, we don't have any voltage measured across the output. During the next positive half cycle, there is an output measured, and that this is actually DC. So the AC input has been converted into DC voltage using the diode. If we want to utilize both the positive and the negative half cycles of the input waveform, then you can simply have two diodes, so that one conducts during the positive cycle and the other one conducts during the negative cycle. So we can have diode 1, and then we can also have diode 2, D2. And then maybe we can have, this is our load. Let's use the sender tap. So this is our load, RL. So during the positive half cycle, this cycle, D1 conducts, and the output is like that. Current through the load will be in that direction. During the negative half cycle, D2 is forward biased, D1 is reverse biased. So D2 conducts, but current is still in that direction. So like that. So you may notice that during both cycle, the negative and the positive half cycle of the input waveform, current through the load is in the same direction. Same direction meaning that it is a DC voltage. So that is how the diode does rectification. With the output waveform, it's actually an output, but it has some ripples. But to remove this ripple, we use what we refer to as the filter circuit, so that you can be able to obtain a pure DC across the output. So that marks the end of our lesson. Thank you very much.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.